Project Euler problem 250, back again with the same 4 AI models, but only one correct approach, and 3 that technically work but really shouldn't. Today we're going back to break down exactly what each model produced and why the differences matter, along with what separates a truly clever solution from a mathematical one. Here's the problem. You have a set of 250 elements where each element is a number raised to its own power. 1 to the power 1, 2 to the power 2, 3 to the power 3, all the way up to 250 raised to the power of 250. That last number alone has more digits than atoms in the entire observable universe. You need to count all the non-empty subsets whose elements sum to a multiple of 250. And because the final digit is so astronomically large, you only report the last 16 digits. And unsuspectingly, the factorization of 250 into 2 and 5 cubed turns out to be far more important than it looks. 4 models and 4 distinct strategies. Claude immediately went for polynomial ring algebra, a framing that most people wouldn't even think to use here. Gemini correctly identified that the sequence has a period of 500 terms and used that, plus another extra trick. And ChatGPT also found this period of 500, which is a genuinely good observation that increases efficiency drastically. But it didn't actually exploit it to the complete potential. Grok went for the most direct approach, looped through everything, update a table, but all of this seems kind of arbitrary. Let's look at what exactly each of those mean. Grok's approach is the most straightforward. Set up a DP array with 250 slots and loop through all 250 elements one at a time. For each element, compute its residue mod 250 and then shift the array. That's it. No pattern finding, no mathematical structures, just iteration. The code is clean and easy to read and simple to verify, but it doesn't reduce the total work. 250 elements times 250 array slots equals 62.5 million basic operations. Rather than a direct approach, ChatGPT noticed something else. The sequence k to the k mod 250 repeats every 500 terms. So instead of processing all 250 elements individually, it builds a frequency table and counts how many times each residue appears across the full set. That's actually a sharp observation, but the problem is what comes next. Rather than using that structure to batch each computation cleverly, it loops through each residue one time for every occurrence. So the total iterations are still 62.5 million. So the period was found, but it wasn't used effectively. Gemini starts in a very similar way. The same frequency table with the same period detection, but it adds one genuinely clever step. Some elements have a residue of 0, which means they don't shift the sum at all. So if you have 501 such elements, you don't process each separately. You just multiply the entire DP array by 2 to the 501. So that's a real mathematical insight, distinct from the ones that ChatGPT and Grok found. The catch is that for all non-zero residues, Gemini still iterates one by one. So it's partially optimized in one case, but unoptimized everywhere else, making it an extremely efficient solution, but not the most efficient that's possible. Claude reframed the entire problem. Instead of thinking about elements and updates to DP arrays, it thought about polynomials. The idea is this: you can encode the whole subset counting problem as a polynomial product, where the exponent on each term tracks the running sum mod 250. Then you multiply all 250 of those polynomials together in a ring where x to the power 250 equals 1 and the coefficient of x to the power 0 tells you exactly how many subsets sum to a multiple of 250. That's the setup. Now here's where the actual period idea comes in. Because the sequence repeats every 500 terms, you don't need all 250 polynomials separately. You just need the product for one period and then you raise it to the right power, and raising a polynomial to a large power is a problem with a very clean solution. So before we get into the details of Claude's code and the detailed algorithms and methods that they use to solve it efficiently, we can look at the more naive approach that gives us an understanding into how the problem actually works. So you keep a list of 250 numbers. The list represents how many subsets give each possible remainder when divided by 250. You start with just one subset, the empty set. So the first slot is 1 and everything else is 0. Then for every element in the set, you go through the whole list and shift things around based on what the remainder that the element adds. Do that 250 times and you're done. It's slow because you're doing 250 passes over a list of 250 numbers, but it still works. ChatGPT and Gemini notice something that cuts that down. The remainders follow a pattern. After 500 elements, the exact same sequence of remainders start repeating. So instead of 250 things individually, you can count how many times each remainder appears across the full set and then group them together. That's what the frequency table and DP array does. So you've gone from 250,000 individual steps to just 250 groups. But the problem still is that both models process each group by updating the list one element at a time. So if the remainder 4 appears 500 times, they loop through the update 500 times. So the total work still ends up at around the same. But Claude's code does something differently. It treats each update step as a polynomial multiplication rather than a list update. So when you update the list for one element with remainder r, you're essentially multiplying a polynomial by the term 1 plus x to the power of r in a ring where x to the 250 wraps back to 1. So if you apply that 500 times for one residue, it's the same as raising a polynomial to the 500th power. And that's a well-known trick, repeated squaring. Instead of multiplying 500 times, you just square the polynomial and then square the result and then square that and then keep going. So after just 9 steps, you've computed the 500th power. And that's the entire insight. It's just repeated squaring, a concept that we all know, but an extremely unique way of applying that concept to solve an extremely complex problem. So comparing the chain of thought in each of the model, it makes the gap in reasoning visible. Claude's chain has 8 deliberate steps, each one building from the last, from Chinese remainder theorem decomposition to fast exponentiation. Gemini and ChatGPT both have 5 steps with the period inside at step 1, but nothing sharp after that. Grok has the shortest setup array, loop, done. The length isn't the point, the depth of each array is. Let's look at the numbers. Runtime, Claude at 0.23 seconds, Gemini at 5.1, ChatGPT at 12.6, and Grok at 14.7. On mathematical depth, I would say Claude scores a 9.5. It's the only module that used the completely unique method of polynomial ring algebra to reframe the entire problem. Gemini is a solid 7. The period detection and the 2 to the f trick for 0 residues are genuinely good mathematical contributions and not guessing. ChatGPT gets a 5. They did find out the 500 repetition period, but it just wasn't used to the most capable manner. Grok scores a 2.5. It's correct, but it doesn't have a unique structure and simply loops through the entire list. Creativity follows a similar pattern, but readability completely flips the table. Grok scores an easy 9 out of 10, just 15 lines of code that anyone can read, understand, and verify under a minute. Gemini scores an 8. Claude, despite being the most effective solution, actually scores the lowest on understandability and readability. Because if you don't have a number theory background on polynomial rings, and the overall setup would just look like gibberish. The full comparison table makes this clear. As you can see, Claude wins on the performance, but Grok wins on the explanation and the simplicity. Gemini is the most well-balanced out of the 4, having good readability and a decently well-rounded solution. To make the speed gap concrete, in the time Claude finishes, ChatGPT has done about 1.7 million loop iterations, but Grok hasn't even hit halfway. So it's not a hardware difference, it's just 111 times fewer fundamental operations, which no amount of optimization and hardware changes can actually close. So overall, I would say the best solution is Claude. The runtime speaks for itself, the efficiency is unheard of, but I think the real win is the method they used and the creativity of the solution. Seeing a subset counting problem as a polynomial exponentiation is not the obvious move, but it's worth noting that if you handed these 4 solutions to someone who needed to audit them quickly, they'd definitely reach for Grok first. Even though the worst solution is Grok, it's the lost on runtime, depth, and creativity. It wins on readability and is actually worth acknowledging due to its understandability and ability to convey a complex problem in an extremely simple manner.